Welcome to this lecture series in number theory. In this lecture, we'll look at a very interesting puzzle and we will solve that puzzle by means of the notion of inverses. Alright, so let's recall a few things. We discussed what is the meaning of a common divisor between two integers. So if a and b are integers, a common divisor of a and b is just any integer, non-zero of course, that divides both a and b. So that's very simple. And we say that two integers a and b, not both 0, I should have written it here. Two integers a and b, not both 0, are called relatively prime if the only positive common divisor between them is 1. So we discussed this and we saw as a fact, as a theorem, that fix a positive integer, in fact fix any non-zero integer n, doesn't have to be a positive integer, fix any non-zero integer n and some integer a, then a has an inverse modulo n if and only if a is relatively prime to n. So what does this mean? It just says that you can solve this congruence. You can find an integer x satisfying this congruence if and only if a is relatively prime to n. One direction of this theorem was pretty easy. If you assume this congruence as a solution, then it was very easy to show that that a and n are relatively prime. But the other direction was not easy. I mean, the proof that we gave was certainly not easy. As we promised, later in the next module, in fact, we will give a very short proof of the hard direction. But for now, we will just assume that we know this. I mean, we proved it in full detail, but as I said, the details were optional. Okay, so let's proceed. So what is the puzzle? Fix a positive integer n, and we are given n bins. So n baskets, and each basket has in it some number of balls, some finite number of balls in it. It could also be empty. We are not insisting that every basket has a positive number of balls in it. It could be empty. Okay, so n such bins are given. And now, suppose a is some integer in this range, some positive integer of course, in this range. And at any step, Alice is allowed to choose any of these a bins and add one ball to each of these bins. So Alice has an infinite supply of balls with her. She has been given an indefinite amount of balls. And the game that she is being allowed to play is that at any instant, at any step, she is allowed to choose a of the bins and add one ball to each of them. Now her challenge is to, so here is the theorem that, or fact that we want to prove, that if a and n are relatively prime, then Alice can equalize the number of balls in each bin in a finite number of steps. So let's try to understand what are we asking. So in the, before Alice started doing anything, each bin had a certain number of balls in it. Okay, and that could be any number chosen by the adversary. The first bin could have 5 balls, the second could have 7 balls, and so on, whatever, like just some fixed, and some number of balls in each bin is given to Alice. Alice can look into the bin and count the number of balls in each bin. And now the, Alice is allowed this move, that at any move, she can choose a of the bins and add one ball to each of them. And the challenge is that she wants to equalize the total number of balls in each bin. Can she do it? Well, we want to prove that she can do it if it is given that a and n are relatively prime. A is a fixed number. She is not allowed to change a. So the simplest example of this was when a were equal to 1. If she is allowed to choose any one bin and add a ball to it, clearly she can equalize the number of balls in each bin, right? So that's trivial, but it becomes interesting when you do not have a equal to 1 and you only have this hypothesis that a and n are relatively prime. So this is the puzzle, And let me illustrate it in a concrete example. So this time there are 5 bins and Alice is allowed to choose any 3 of them and add 1 ball to each. So here is our indefinite supply of balls. Let me color them a little differently so that we can see. Okay. So what is Alice allowed to do? So this is the initial configuration of balls. The adversary has chosen this, and now Alice is challenged to equalize the number of balls in each bin by, what she's allowed to do is choose 3 of the bins and add 1 ball to each of them. So in the first step, she might choose to add 1 ball to these 3 bins. So she will add 1 ball here, add 1 here, and add 1 there. Still, equalization hasn't happened. This has 2 balls, this has 1 ball, 2 ball, 2 ball, 3 ball. So everything is not equal. So she might then maybe choose to add, let's say, 1 ball here, 1 ball here, 1 ball here. So these 3 have been equalized. These 3 bins have the same number of balls. But here, no. And we are in a little bit of a pickle. If you add 1 ball to this, 1 ball to that, and then 1 more ball to something else, you would still not have equalized. So what we want to prove that it can be done. If you do it intelligently, if you choose your 3 bins in some intelligent way, then in a finite sequence of moves, you would be able to equalize the total number of balls in each bin. Okay, so I encourage you to think about it. First, perhaps try to solve this particular example somehow, and then consider more examples of your own to get a feel for the problem, and then try to prove it in general. So that's, of course, something that you should do. And with that, I want to now show you my solution. So let's illustrate the main idea in this particular simple example of 5 bins and 3 choice of 3 bins at a time. And let's say, for just the sake of understanding, that all the 5 bins were initially empty. We are going to do something which will show us that no matter what is the initial configuration of balls, doesn't matter. So here is what we are going to do. We are going to go about this in a cycle. So first we will add 1 ball to each of, what am I doing? This is not what I intended. So this is 3, 4, and 5. Yeah. So they are arranged in a cycle. I've just labeled the bins by numbers 1, 2, 3, 4, 5. And now we'll add 1 ball to each of these bins. Then, so let's do it. So 1 ball to each of those. And now I'll also add 1 ball to each of these bins. The next 3 in this cyclic order. And what do we find? We find that the first bin has 2 balls, while all the other bins have only 1 ball. So if you do it in this cyclic fashion, just in 2 steps, what we are observing is that you can increment the number of balls in the first bin by 1 count relative to all the others. Right? Everybody else got incremented by 1 ball, but this bin got incremented by 2 balls. So relative to all the others, this bin gets incremented by 1 ball. And therefore, in every 2 moves, you can increment any chosen bin, any bin you like, by 1 count relative to all the others, because the numbering is up to us. We can number these 5 bins in whatever way we want. Okay, so that is the main idea. Once you have this observation with you, clearly you see you can equalize. If you have the ability to increment the number of balls in your chosen bin by 1 count relative to the others, it is as good as saying that you are able to choose 1 bin and add 1 ball to it. Right? So I hope you understand that this solves at least the simple case of n equals 5 and a equals 3. There, this shows that you can equalize no matter what is the original configuration of balls in each bin. Let's look at this same solution in a slightly different light. So again, we have a as, I've taken a as 2, but okay. So let's do it for 2. We will also do it for 3 perhaps. I somehow, mangled the thing. So suppose you're able to choose 2 boxes at a time, 2 bins at a time, and add 1 ball to each of them. So what we will do is we'll kind of depict the boxes in this cyclic fashion. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 that way. And in the first step, we'll add one ball to each of them. In the second step, we'll add one ball to each of these. And in the last step, or in the third step, we'll add one ball to each of them. So here, this is same as that. It's not like this is a different bin. It's, it's just a representative. So we'll add one ball to here, but this next ball will be going to the bin number 1, even though it looks, a little different in this depiction. So it will go actually here. So in this in these three moves, we are able to increment the first bin by 2 counts, while all the other bins by 1 count. And hence, the first bin gets incremented relative to others by 1 count. Let's maybe also do it for a equals 3. It will take me some time to arrange everything. Okay, so this time we have n as 5 and a as 3. And again, we will increment in this cyclic fashion. The first 3 will be incremented by 1 count, and the next 3 in the cyclic sequence, so this one is the same as that one, we will increment by 1 count. And just to show you, this is how it's going to go. And the next thing goes here again. So in this process, the first one gets incremented by 2, while all the others are incremented by 1. Let's see the same thing in a slightly more complicated example. This time n is 7 and a is 3. And this is how we will increment. So we have enlisted the 7 bins in this fashion, the 7 bins, and then the 7 again, and then the 1. So we will increment this way. 4, 5, 6, and then 7. And then this is actually going to that guy, right? Because it's going to the bin number 1. Then bin number 2, bin number 3, number 4, number 5. This goes to number 6. This goes to number 7, and then this again goes to number 1. So the first bin gets incremented by 3 counts, while all the others get incremented by 2 counts, right? So the first bin gets incremented by 1 relative to all the others. And you can do this with your bin, chosen bin, your bin of choice. 1 is just an arbitrary labeling. Right, and what is going on here, if you notice, is that we have used the fact that there is an inverse of 3 modulo 7. What we have is 3, a is 3 times 1, 2, 3, 4, 5. 3 times 5. 3 times 5 is congruent to 1 modulo 7 is all that we have used. Right? 3, 3, 3, 3, 3. You go in the cyclic fashion. Because of this excess of 1, you are seeing that this guy gets incremented by 1 extra. That's just a bunch of words that I've spoken, but I hope you're able to relate with the picture. Right? If 3 times some number was congruent to 0 mod 7, then doing this in this cyclic fashion would have incremented everything by the same amount. But because of this 1 excess, we are able to say that we are incrementing one particular bin by 1 extra. So that's basically the idea of the proof. And I don't want to give or write down a general proof in the general setting. I'll just say the same thing towards the general proof. I'll just say this, and this is not really a rigorous exposition of the proof, but we are given that a and n are relatively prime and all those things that we discussed. So first find a positive integer case such that this happens, and we can do this because inverses exist precisely when a and n are relatively prime. So there is some inverse, and we can choose a positive inverse, of course. You can choose a positive k which does this. And now in k steps, you will be able to increment your chosen bin by 1 count relative to all the others. That's what we illustrated in the previous page. And I want to leave it at that. I do not want to write down a formal proof for this particular statement. I don't think it will help. The main idea, I hope I have illustrated sufficiently. And if it is unclear, then I encourage you to stay on it. And better yet, if you had find your own proof, that's the best. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.